Okay.
Okay, well, welcome to everyone. Thank you for attending the special lectures from the Pittsburgh HoTT seminar. It's a pleasure to have such a large attendance today. I want to thank Denis-Charles, Kim, and Tashi for agreeing to give these lectures. We're very curious to hear about their work and their advances toward a type theory for categories. So the talk is going to be an hour and a half, and then we're going to keep half an hour for discussion. So don't hesitate to interrupt the speakers for questions or remarks or anything. And so now the stage is for Denis-Charles and Kim that are going to talk today.
Thank you very much. So we start with so thank you for this opportunity to explain our joint work. And I will start with an introduction, and then Kim will take over to start to give the list of axioms. So sorry for the mess for sharing. So the goal is to provide an axiomatic to do category theory, but in a synthetic way, the same way homotopy type theory does a synthetic homotopy theory. And the idea is simply to use a type theory, but we won't take the full package of dependent type theory because we cannot have all dependent products. And it will be also an extension because we have to speak of arrows, and therefore it's quite natural to introduce an object which will represent the idea of arrows. For instance, we have new constants. And the goal is really to try to formalize category theory in some sense. So how do we change this? Okay, thank you. So here is in a nutshell the kind of thing we want. So I'm it will be very rough because then the goal would be to introduce the axioms carefully, and so here is just to give an idea. So there should be a type theory where a type, I mean a category, as opposed to a set or a groupoid or an homotopy type. And for instance, there should be like in ordinary category theory, you should have the free completion of the point by colimit and the pointed version. And of course, the goal is that these expressions should make sense, like the free completion by colimit of something should make sense in this type theory. And we would like that for getting the base point from S dot, so the pointed version, the cos slice of this free completion of the point should be a fibration, and this fibration should classify groupoids, where groupoids should be types in which all edges are invertible, which should be also something we want to be able to express. And this correspondence should be functorial, and not only for isomorphisms, but also for non-invertible maps. And this is what directed univalence should express in some way. So it should be a particular case of what we call straightening. And of course, we want to express all the basic results of category theory. So for instance, the Yoneda Lemma that I did try to convey in the middle of the slide. And from there, once you have the Yoneda Lemma and a good theory of straightening, then we should be able to develop all the basics, so in particular the theory of Kan extensions and pointwise Kan extensions that can be expressed in terms of limits and colimits and so forth. And of course, this straightening, we want to extend to co-Cartesian fibrations, which should be also something that makes sense. And so we should have a correspondence between co-Cartesian fibrations from X to A and pull back from a universal co-Cartesian fibration. And again, it should be functorial in a suitable way. And that should be a directed univalence for this universal co-Cartesian fibrations up to smallness issues. And we should have all the usual properties we have for basic category theory. So for instance, we would like to know that the equivalences are exactly the functors or the maps, if you want, which are fully faithful and essentially surjective. We would like to know that if we restrict to groupoids, the theory should give back ordinary dependent type theory. with univalence. And therefore, we should be able to interpret homotopy type theory, and therefore also to use it. That means all the theorems we already have in HoTT, we can use them to actually understand equivalences in there. And of course, we would like that this theory to be usable, in particular, in either way, in ordinary mathematics, I would say. That is, whatever you prove in the formal system should be a theorem in mathematics. But we will also to provide semantic interpretations in ordinary mathematics is also a way to check a soundness of the axioms we provide. Yeah, and the idea is that the theory of quasi-categories, the way they have been introduced by Joya and then Lurie, is really a semantic interpretation of the theory we want to introduce today. And in some sense, the proof that it is a semantic interpretation is an extension of the Voevodsky's proof that Kant complexes form a semantic interpretation of dependent type theory. So this semantic interpretation is somehow the first thing I've worked on. I mean, I wrote a book on higher category theory, and it was designed more or less so that this proof would happen. And so now we will develop the formal logic of which quasi-categories will be the semantic interpretation. Of course, there are many other ways to axiomatize what is a category theory. So there is at least the work of Cosmoy, of Riehl and Verity, and what we present will be very closely related, possibly slightly weaker in the sense that we don't really need to have a strict type formers, completely less strict operators to express ourselves, but otherwise it's very, very, very close. And the interest also is that we won't have semantic interpretations, ordinary infinity one category theory, but also other instances such as infinity one categories seen internally into any infinity topos, for instance, would be a semantic interpretation. Yeah. So maybe, so here I've tried to convey what should be the basics, what we should start from. And then I propose to give a list, it is not exhaustive at all, of the kind of thing we should expect to be able to prove if we form, and that means to formalize as a consequence of the axioms. And so you see there have two first groups, which is HTT is for higher topos theory. It is a reference to the Lurie's book. And HA is also a reference to Lurie's work, higher algebra. And what I mean is that there are very large portions of these books that we should be able to actually develop as theorems in this formal system. And that should include the theory of presentable categories, the theory of topos themselves, the theory of stable categories, T structures, weight structures, derived categories of abelian categories, the theory of operas, Beck's theorems. Something that Lurie addressed a little less, but I like to address myself very much, which I also do in my book on higher categories, that all the methods we have about model structures and using that to derive functors and so forth can be done in this kind of setting. We already know that we can have a theory of infinity model structures by Mazel G, for instance, and that means, and this can be extended to directed types, whatever that means. And something which is interesting enough, but that should make sense in this very formal setting would be, for instance, all the basic results about the algebraic K theory. Should be part of basic results, formal results we should be able to reach. And then, as you will see, we'll be able to produce the category of simplices in there, and therefore there is no reason to stop short here, and we should be able to formalize within directed type theory some version of infinity n category theory for higher n. So that would be the first list. That would be so far the list is about ordinary mathematics that we want to develop. And of course, as a remark, so when we do type theory, we have a large portion of the literature which consists to see how we have semantic interpretations using category theory, where category theory is intended in classical way. That is, you have a set of objects and so forth. So So using set theoretical kind of foundations. But the idea is that if you have a rich enough theory, which the object of which can be called categories, then instead of trying to produce semantic interpretations using ordinary category theory, we could try to do it in this context. And therefore, we can use the theory to formalize logic itself. And so once we know it is sound enough that it can be interpreted in ordinary mathematics, we can also somehow forget about it and just use the theory to formalize logic itself. And just to give you an idea, which I hope will be clearer after the couple of talks, but I want to stress it just now, and we can come back later to it, is that so we have it will be a type theory. So there will be an underlying category, a syntactic category. So maybe we can call this E. And then for any type, you should think of it as a category. It can form the slice. And of course, usually we don't take the slice, we take the full sequence of the slice whose objects are some kind of vibrations. But then you can take even smaller full subcategories. So you could take what right vibrations, which should correspond to co-Cartesian vibrations with discrete fibers, so pre-shifts in some sense. And then they will define a kind of logic. But if you think about it, it really consists in taking a fragment of your syntax. So you don't even really need to know that you have an actual category. You can really speak of the language. And this full subcategory just means that you actually take a fragment of your language. Yeah, you don't need to go to category theory to say you take the full subcategory, just an image of speech, figure of speech, we say, I think in English. And then you can take representable pre-sheaves, and then you will have a kind of language, an ordinary type theory that will reflect very faithfully the property of your type C. And you can go back and forth within that. So I will come back to this aspect later. So just as a remark is that it is really a way to rectify pullbacks all the time, because we really provide a syntactic one category. It is always possible, in which we will have a notion of vibrations and strict pullbacks. And usually also you will have if you have a universe in C, you will have a strict universe, in fact. But what will be hard to rectify will be dependent product kind of constructions. This will be, you can only see up to equivalence somehow. That would be so you have to, but the idea is that because you have a univalence in a directed way, that means you can really do logic and category theory up to equivalence. This shouldn't be a problem at all, and that by definition of univalence. And so now that I've introduced the general idea of this, so I'm starting to, before we start the axioms, I propose to come back to the setting. So we won't provide the syntactic presentation at first. We do the category theoretic presentation. So we speak of the syntactic category, which we call this E, and this will be our underlying tribe. And so to fix the axioms, so we work with such a tribe in the sense of Royal. So here I just, the slide here, just give you a recollection of what tribes are, for the few of you who maybe don't know all the axioms by heart. So that means you have a category in which, but here, because we want to interpret objects of this category as categories, so the maps will be sometimes called functors. There will be a notion of vibration, because a tribe is by definition a category with a class of vibrations. But because also I think of this tribe as a category of categories, and in category theory, the notion of vibration that is suitable to work up to equivalence are called iso-vibrations. So the vibrations of my tribe I will call iso-vibrations, just to fit with the terminology of category theory, ordinary one. And so these iso-vibrations can be composed, and any isomorphism should be an iso-vibration. And also we can pull them back. So the pullback of an iso-vibration always exists, and this pullback will be an iso-vibration as well. Then you have anodyne maps, which are the maps which have the left lifting property with respect to iso-vibrations. And the axioms is that any map, any functor can be factored into an anodyne map and then an iso-vibration. And also, if you pull back an anodyne map along an isofibration, you should get an anodyne map that is a lower pullback square in the slide. And then we have notion of equivalences, which are the maps which become invertible in the localization by anodyne maps, or the homotopy equivalences. And an example would be, for instance, the category of quasi-categories, for instance. And so now Kim will very soon start to explain what are the axioms in this setting. I would like to insist on the fact that when I describe what is a tribe, you see, it is just a category with a class of maps and then some properties which are very category theoretic. That means that whenever we have produced the axioms and therefore a kind of category theory, we can redefine a tribe as being a type equipped with a set of edges or maps or in which all the axioms are true, and all the axioms we will present to you are robust enough so that they will make sense for a type in this very abstract sense, and the theory will be robust enough to prove that all the theorems you can derive from the axioms can be proved from this more generalized types. But maybe we can come to that later. So I think I finished the introduction I wanted to give, and then I give. So Kip will take over and start the axioms. Maybe.
No. Okay.
To adjust.
Give me just a second to switch setups. Okay.
I guess while we wait, are those notes available, or will they be at some point?
Yeah.
Sorry.
Will the notes be available?
Yes, I can send my slides to my Mathieu, and
that'd be great. Thanks.
Yeah, I'll put them online on the website of the seminar.
I also have a question, if I may, while we wait.
Yes.
Stuff you were talking about at the end when you're talking about the tribes, you're talking about, I think, well, correct me if I'm wrong, how to internalize the theory so that it can eat itself. You're saying we can take this theory, describe it as a tribe, and then that's a structure on an object that we could have inside the theory. Is that the idea? The tribe itself, you're not describing the whole thing from the outside. You're saying this is a small thing that we could reason about inside.
Yeah, I mean, so the tribe will be the logic. So we'll try to. We didn't work out the full syntax of the logic yet, but yeah, we should have a logic like a type theory where types are seen as categories. I don't know.
Yeah.
And the tribe is just because I don't want to. I mean, it's just a shortcut not to. Which allows ourselves not to give the syntactic rule right away.
Okay.
Yeah.
Okay. Thanks.
Maybe I should add a few words. Is that because there is a universe, and you see, in some sense, the universe in ordinary type theory. If you think of types as sets or types as groupoids or homotopy types, then the universe is a set or a groupoid or an homotopy type. And what is happening is that the syntactic category is a category. That means that the logic is it can be described using category theory, but the universe in ordinary dependent type theory is not a category, and therefore the structure of the universe does not reflect, not obviously at least, of course you can reflect a lot of things, but it does not reflect obviously the categorical structure. Because you see, if you think of types as a set, you just have a universe which is a collection of sets as opposed to just being the category of sets. Yeah. So here we have a type of types, but it will be the category of categories. You see, the category of categories is a category, and that means you can really go back and forth between the structure of the type and the logic, and therefore the universe will reflect very, 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 very faithfully the logic natively.
Okay, now I'll try and share my screen. Okay, that works for everyone. Okay, perfect. Right, so I'll start with the axioms. Right, so Denis-Charles already talked about tribes. So let's skip this slide. This is just, again, an overview of the categorical setting that we're working in. So in other words, from a type theoretic perspective, we start with the dependent type theory with sigma types and identity types. And right, so the fibrations here I'll refer to as isofibrations. And what we would like to have is a hierarchy of universes. So, right, that's what's written here. So we have an infinite well-ordered set, and for each member of that set, we want to have a subtribe, and it's supposed to be sufficiently closed under the operations that we like to perform. And just to fix terminology, so if my writing is not large enough, please let me know. So terminology is that an isofibration call that P from X to Y is U small if for any pullback diagram B with the U small, the object A, so the pullback itself is U small. Okay. Right, so then we want to have some further axioms on the tribe itself. One is the universality of sums. So in other words, if we have a finite set J and some family of objects, then we want the sum to exist and that the pullback functor is an equivalence of tribes. So pullback preserves sums, and the pull product, for example, sum of two isofibrations will again be an isofibration. Then the next axiom that we would like to have on the tribe is that we want to have an internal Hom. So taking product admits a right adjoint. Okay, so far nothing out of the ordinary. And now, so as Denis-Charles already said, the point is that we don't assume to have all dependent products, but at least we want to have certain, we will fix certain dependent products which give us enough, say, power to develop the things that we want. So let's start with more recollections. So recall that if we have a commutative square, so then it's a homotopy pullback. If whenever we factorize one of the maps, so we can factorize it into an anodyne, say, followed by a fibration, followed by an isofibration, then the following map is an equivalence. And a map is a, say from A to B, is a homotopy monomorphism if the following squares are homotopy pullback. And more generally, a map is n-truncated if, say, for any 5-point replacement, right, to B, the map A prime to the diagonal is n-1 truncated. So, and say -2 truncated, meaning an equivalence. And an object is n-truncated if object A is a canonical map to the terminal object is n-truncated. Okay, so that sets the stage, and then our first couple of axioms will involve an interval. So we want to assume that an interval exists, which is supposed to be an object denoted here with blackboard bold I, and it comes with 2 maps, which one can think of as the inclusion of the endpoints of the interval, such that the diagonal is both an isofibration and a homotopy monomorphism. That's what should be here. And if we take the sum of those endpoint inclusions, then it's an isofibration and a monomorphism. And then first thing is that we want dependent products along this inclusion to exist. So it's one of the first dependent products that we want to assume to strictly exist. And finally, we want the interval to be 0 truncated. So let's see what we having an interval, what we can define from this.
Sorry, is there a requirement of any relationship between isofibrations and lifting against the endpoint inclusions of the interval?
No. Right. Yeah, I mean, so no. But I mean, so like the endpoint inclusions like will be lifting against other classes of fibrations, and that we want to use the interval to define them.
Is this like, so I mean, in some models of infinity 1 categories, there's like a sort of spatial direction and a categorical direction. I guess I'm thinking of the complete single space model. And you know, the notion of isofibration categorically suggests like that's maybe something in the categorical direction. And is this interval, should we think of it as being in the space direction?
No, I would say it's a category. I mean, you can of course also No, I mean, it's really the categorical direction, because the interval really encodes the direction. So, I mean, the distinction between like the starting point and the end point really is important to us. So that one inclusion is really an initial object that will be one of the axioms too, and the other inclusion is a terminal object. So it really gives us the direction.
I see.
So
Yeah.
we could say
Particularly,
that
you might have a model in mind where the interval does not have a reversal.
no, it doesn't have a reversal at all. So this delta one, it will be used to build the category of arrows. You see, you can take the internal home from delta one, and that will be the category of arrows of whatever you take the internal home of. So it is really non-invertible. It will represent all possible maps as opposed to invertible ones.
Great. Okay. So
And
that,
of
okay.
course-
Very good. So this interval represents an arrow, not a.
Yeah.
Exactly.
Very
Yeah.
good. And so the 2 is giving you the join then.
Yes, exactly.
Yes. Great.
Yes, exactly. Right. So let's start and try and do something with the interval. So we can define deformation retracts, and really giving the deformation retracts a direction. So it really matters if we are moving like from the identity to the deformation, or from the deformation to the identity. So let's make this precise. So a right deformation retract is a map call it S for section from A to B together with further maps from B to A and a homotopy. Such that the one S is a section of P, so that's supposed to be the identity in A. Then the homotopy moves from the identity on B to the composition. So this is supposed to commute. So in other words, we have really like a 2-cell, and the homotopy is constant on A. So it's the usual notion of deformation retract. Take a projection. Here's the homotopy. And this commutes. And dually, we can define a notion of left deformation retract where the
Sorry, one
homotopy
more.
goes.
Okay, I keep interrupting.
Sure.
Is there any requirement that P of H is also trivial?
No, no.
Okay.
Yeah.
In the quasi-category model,
Yes.
is that a reflective, full reflective subcategory, so to speak?
Yes. Yes.
So that's-
yes. Yeah, sorry. So that's kind of our point. We want to say we want adjunctions, but at this stage we cannot really say this. But the deformation retracts are precisely fully faithful adjoints. So the right deformation retracts should be fully faithful right adjoints, I hope. And the dual notion, the left deformation retracts, should then represent the fully faithful left adjoints. But this is really kind of trying to avoid saying adjunction at this point, because in the end, an adjunction, what should be, it should be a fully functorial notion that we cannot say at this point yet. But so far, for at least for introducing the things that we want, these deformation retracts are good enough.
So sorry, I think the condition on P of H is the other triangle identity. So it appears to me that you're missing one.
Yeah. Okay. That might be possible. Yes. Right. Thanks. But yeah, it should be like the usual notion of deformation retract. Yeah.
So H is the unit here.
Yes.
Am I understanding correctly?
Yes.
Yeah.
Yes. Exactly. Yes.
Yeah. Okay, and the co-unit is trivial, and so the triangle identity is reduced to something like H pre-composed with S is trivial, as is H post-composed with P.
Yes. 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 Yeah. Okay. Thanks.
I don't know. Maybe a different terminology would be to call that a reflector or a co-reflector, rather, because it's somehow we are in the model of quasi-categories, not in homotopy theory anymore. So that would be a way to maybe adapt the terminology to this, maybe this context. But that's just a suggestion.
Yeah. Thanks. Yeah. I mean, I don't think we have very strong opinions on terminology just yet. So yes, thanks. Yeah, sure. Right. So then the dual notion should be even more precise, I think. Right. So sorry. So that's like the inclusion of the starting point, and that's the inclusion of the end point. Right. So then there's a dual notion which one can work out. So dually, there is a left deformation retract. And really, the direction really matters here again. So one representing right and adjoints, and the other representing left adjoints. And then we can use this already to define, say, what final and initial objects are. So it's called map final, respectively initial, if it is a right, respectively a left deformation retract. Okay. So then further axiom on the interval is that we have connections on them. So the map, the inclusion of the starting point is a right deformation. Sorry, that one is a right deformation retract, and the other is a left deformation retract. And I think I just switched here directions. So right deformation retract should be a final object, right? So I mean, okay, so let's just read this simplically. Yeah. So it's a void zero, so it's inclusion of the endpoint. So it's a final object, and here's the voids one, so it's inclusion of the starting point. So simplicial convention, it's correct. Okay, so that's this will be another axiom. So in other words, so let's just write this out. So this has final and initial object. And so basically the structure of them being deformation retracts just means that we have connection on the interval. So in this case, it will be the maximum connection and the minimum connection. Okay. And then, So remember, I want to talk about the third property of the interval, namely that the pattern product along these maps exists. So this will give us a join operation on the interval, on the tribe. So let's talk about this. So we have pullback along I that should give us a map like so. And the pattern product says that we have a right adjoint to it, and this preserves the tribe structures. So we have a morphism of tribes. So for objects, say A and B of our tribe, we get an isofibration. Over the interval, and then define total space of this. As the join of A and B. And it's characterized by the following properties. Well, so let's just write down the obvious. So it's a functor. And note that the join of the terminal object with itself, that just gives us back the interval. So we have this isofibration. I'm just collecting all of the information. And we have canonical pullbacks. So and the join has a universal property, which is given by following. So a map to the join determined by an isofibration to the interval with two maps. And these are the fibers at 0 and 1. So fibers at starting and end point. So this corresponds to following diagram. There's our I. So given such a commutative diagram, I get this in this map. Okay, now using this joint construction, what we want to do axiomatically is define simplicial objects in the tribe. So there are some more axioms on the interval, this time defining a simplicial structure. And what we'd like to have is an isomorphism where we join the terminal object either on the left side or on the right side of the interval. And in a way such that the following square commutes. So here is just the isomorphism coming from the coproduct, and it sort of should be compatible with this associativity isomorphism. That's what this this commutative square expresses. And furthermore, so we have kind of like an associative isomorphism, and we would like this to satisfy the pentagon axiom. So let me try and explain what we mean by this.
Maybe a question?
Yes.
So at this point, you have the binary join operation, so to speak, a functorial operation. It's a kind of tensor product, but you need this associativity isomorphism somehow to construct an associativity isomorphism for the joint product?
Yes, exactly.
Okay.
Yes.
So
you
this
want
is
to join in the end? Yes, I'm sorry.
And the associativity isomorphism for the join will be up to isomorphisms in the tribe?
Yes, for the moment, yes.
But you have to recall the axioms is that the interval is zero truncated.
Yes.
So therefore, you see, at least if you restrict to joins of points, we are looking at maps between zero truncated objects.
Okay.
And so the idea is that we can stay very low in coherence problems.
Okay.
So you could work with equivalent up to equivalence. In fact, that's not a big deal here.
Okay.
It just happens in usual models. It is an isomorphism, like literally, but you could say equivalence. It doesn't really matter.
I'm not objecting. I'm just curious of what you're doing.
Yeah, exactly. I'm not saying the object. I'm just saying that we have a kind of freedom, and I like it. I share it.
Okay.
Okay, let me still just let me still just trying to explain, although it seems to be clear already. So explanation is that well, so given objects, say A, B, and C, then we have a commutative diagram. So I'm doing the same diagram as before, just replacing everything with arbitrary objects. But the point is that having this associator really gives us an associator isomorphism. So I can take either the join of B and C first, or the join of A and B first. And this maps down here. And so in particular, by the universal property of joints, we get such a map. And this induced map is itself an isomorphism. Okay, now so if we apply all these different notions of associator to the case of the terminal object, then we can write down the pentagon axiom. And one of the so what we mean by this sentence here is that this pentagon axiom, this pentagon commutes. So we obtain which is just this sequence of joins and this receives a map. This should be this one, and further maps. And this is supposed to commute. So Simplicial structure axiom asserts that this commutes. And the point is that as a consequence, we obtain that this pentagon axiom commutes for arbitrary objects, and thus the join defines the monodal product in the tribe E. So this implies that all of these maps satisfy the pentagon, i.e. the join defines a monodal product on the tribe E. And moreover, this is also saying that terminal object is a monoid. With respect to the join. So using this, we can define simplices by just inductively taking joins of terminal objects. I'm gonna call them delta n with a subscript of the interval. So really saying that it comes from the interval, but I'll drop this soon enough. In any case, you can define delta minus 1 to be the initial object. And delta 0 to be the terminal object. And by induction then So in particular, we have that the interval itself is just delta 1. And then, so this terminal object, or delta 0, is then a monoid object. We have this canonical map from the initial object to it, and this canonical map. Turning this into a monoid. Right, so the point now is that because we have this monoid in E, we obtain a functor from the free monoid. So we obtain a functor to E. And in particular, what this will give us is simplicial maps.
The domain of the functor should probably be delta plus. It's like they're augmented.
Yeah, augmented, right. Okay, now that we have basically simplicial operators in our tribe, we can define Segal conditions. So this will be our next axiom. Yeah. Further questions or comments so far?
Maybe I have a question.
Yes.
The axioms, maybe coming back to a few pages before, the axioms that the pullback functor along the inclusion of one coproduct 1 into I, that's one of the axiom, right? That the pullback functor has a right adjoint.
Yes.
Yeah. You may be aware that actually, if you slice E over I, if you consider the category E over I, then it is Cartesian closed.
That's.
I mean, because to say that the pullback functors has a right adjoint is actually just saying that the map I from 1 plus 1 to I is exponentiable, has an object of E over I. But actually, in the model of quasi-categories, the Azov vibrations over I, E over I, is actually Cartesian closed.
That's
it's
true.
not true. It's not true in general, of course, that if you slice cat, let's say, let's consider the case of cat. If you slice cat by a small category C, then it's not true that cat over C is Cartesian closed, but cat over I is Cartesian closed, and in particular, this map, yeah. I just want to observe that, which is something maybe that you already know. This is something that that's a general phenomena for not only for quasi-categories, but also for n quasi-categories. That if you slice n quasi-categories over a generating cell of, you know, there are higher cells. I here is the one cell, is the basic one cell. But if you do that in in n quasi-categories in the sense of ARA, for example, then you get the same phenomena.
Mm-hmm. Yeah, I wasn't aware of the higher effect. Yeah, thank you.
Okay.
Yeah. So let's.
Okay.
Yeah. Thanks.
Okay. End of my remark.
Okay. Yeah. Yeah. Thank you. So we were here having the simplicial functor, or having a functor from ordinals to E, which allows us to find simplicial maps in E, and thus we can define Segal conditions, and that's our next axiom, is that we have the Segal maps. So first of all, if we have an isofibration and we're looking at the phase maps, then we want to have again isofibrations, and furthermore we would like the Segal map to be a trivial fibration. And then, having Segal conditions, we get the composition operation in the usual way. So the usual composition operations. By choosing sections. So we have functors from delta 2 into, say, an object X. And here we take the following phase map, which should send a composition to its composition, right? And so that's a map to the arrows. And here we have a trivial fibration to the fiber product. And choosing a section gives us a composition operation. And in particular, this allows us to find a category associated to an object of the tribe. And let's call them homotopy categories. And this can be done as follows. So, as was already mentioned, we really like to think of the interval as arrows. So mapping from the interval, maybe that's mixing up notations. So mapping out of the interval into an object should really represent the category of arrows of the object X. So then simply find the following pullback, and this should be then thought of as the object representing morphisms from A to B. And then define the homotopy category of X to have objects have points in X, and morphisms should be homotopy classes. Of maps of points in this object of more arrows from A to B. And where we can actually use this to define a two-category associated to the tribe.
Sorry, can I interrupt and ask two more questions real quick? Firstly, would you remind me how you define trivial fibration?
Oh, it's an isofibration and an equivalence.
And equivalence was in the sense of the zero equivalence or something? Or
So equivalence, it comes from the tribe, right? So you can, if you have path objects, because you can factorize the diagonal, and then it's just an homotopy equivalence.
Great. Okay, thank you. And then secondly, so I think in your sort of Segal interval axioms, you asked that the map from an n simplex, mapping out of an n simplex to mapping out of any of its faces, that map is an isofibration. Is that right? That was the previous page.
Yes.
So does that imply that the map, to the matching space is also an isofibration? So I thought it was slightly stronger to ask it. I mean, I'm wondering how we know this map to x times x from fun delta 1x is an isofibration. That seems slightly stronger to me.
Yes, I mean that should be a particular case of this.
Oh, okay. I'm sorry. I just didn't understand this definition correctly. Okay. Great. Thanks. I didn't see the pullback there.
Yeah. Right. Right. Yeah, so that's kind of the point, that ultimately we would like this to be like the dependent home type whenever we are ready to understand what that means.
Maybe a question?
Yes.
So your Simplicial, your delta or delta plus is kind of external in the sense that your Simplicial objects are somehow defined externally. I call this externally because the number n in delta n is just an ordinary natural number. It's not at all internal. So I'm just curious, are you going eventually to describe the category delta internally?
Yes.
Eventually.
Yeah,
Yes.
we will. I mean, eventually, we will ask for a natural number object. And therefore, we can produce internally the collection of all the delta n's. And we can do that in the universe. And if we will introduce enough operators so that you can define the full subcategory of a type or the full subtype of a type. And so we'll be able to define, because of univalence, the full type of the universe whose objects are the simplices. That would be delta internally.
So delta then will become an object of the tribe.
Yes, it will be a full subcategory of the universe, and therefore we also correspond to an object of the universe, because it's small in any sense.
Okay. Great. Thank you.
Okay, so not quite there yet, but we can at least define something like a two-category from E by setting, we're taking the homotopy category of the internal home, right? And yes. Then moving on, we can define groupoids. Is a groupoid if the map canonical map induced by just the canonical map to the point is an equivalence. So groupoids should see the interval as a point. and would like to note well, this should be the full subcategory on group points. And further axiom should say that we can basically we can take maximal group points of objects. So the inclusion of the group points into the tribe, this has a right adjoint, which is a morphism of tribes. And furthermore, what we would like to demand is that this map is an equivalence, and that's this. So there are no automorphisms in the interval. That's what this is saying. And now
another question.
Yeah.
An alternative maybe description of what a groupoid could be would use exponentiation by delta 1, somehow saying that an object x to the power delta 1 is equivalent to x via the diagonal. So that looks a little bit stronger than your definition, but maybe you can prove it's equivalent.
Which diagonal do you mean? I mean, isn't that somehow what I wrote here? I mean, if you think of constant maps as like, if you think of this as being the diagonal functor, is that what you're saying?
Oh, yeah, I think so. Maybe I misread your definition. That's your definition, actually.
Yes.
Okay, because fun is the exponentiation, right?
Yeah, right.
Okay.
Yeah.
Okay. Yeah, so I'm curious. You want to write it fun because you think of it as functors, but actually any map is a functor. So you may, yeah, okay, fine, okay.
Yeah.
Thank you.
Sure. Yes. Right. So now in principle, we have two ways to talk about really groupoid kind of things. So this definition of seeing the interval as a point, but then we also have the notion of using the Segal maps. Basically, we can also define what it means to have an inverse. And the next axiom should say that these are the same. So let's try and work this out. So using the Segal maps, I'd like to define an object which is basically witnessing that we have inverses. So I can take functors from delta 2 into x and take the fiber product and I didn't really work out what the right phase maps are, but it should represent the following situation. So we have two simplices glued along the diagonal. It should be. I hope it is. So should look like this. That's sort of like an object represented in this fiber product. And here we can map down into this product, and it's basically picking out the upper corner arrow, the upper arrow and the lower horizontal arrow.
I think in your picture,
And
the right, I think in your picture, the right vertical arrow has to point upwards.
Oh, it does? Okay. I'm fine with that. And
Are
yeah.
you now somehow looking at the arrows in X that have a left and a right inverse?
yes, yes, exactly.
Okay, and you're describing the constructions of this
Yes.
category. Okay, thank
Yes,
you.
exactly. Yeah. That is exactly what I'm doing. So, and the point is then being a group, or it should be the same thing as having witnesses that you have a left and a right inverse. So here, I just take the diagonals, which cross the these two identities, and then what should come out is exactly having a left and a right inverse. So if I take the pullback of this, it's I'll call this is invertible, right? And this receives a map from X. And it also maps to fun delta 1. But right. So that's the object witnessing those arrows which have a left and a right inverse. And then finally another axiom should be that for any object now called C, the canonical functor from C to is invertible is an equivalence. That's kind of like a completeness condition, and then the point is that it relates having inverses with our previous definition of being a groupoid. And this implies in particular is and now I didn't keep track of what is an isovibration, so it's at least up to equivalence, a path object. So what we have is we have C, this maps into its inverse C, and here this also maps here. And then up to homotopy, at least, we get commutative triangle. This is by assumption equivalence. So, hence, C is a groupoid if and only if this map is an equivalence. So in other words, if and only if maps have inverses, and this should relate basically these two notions of groupoids that we have. And then finally, I think the last axiom that I should state for today, and then we want to be able to form full subcategories of things. So that's a full subtype former. So basically what we want to do is we want to say that given a sort of like set of objects, we want to take the full subcategories by this, but that doesn't quite make sense. So what we do is we're given an object and we would like to have a homotopy monomorphism of groupoids. Then this homotopy monomorphism of groupoids should come from a functor, which then is supposed to be the full subcategory spanned by the groupoid X. So there is a functor, and this is supposed to be the full subcategory spanned by X, such that when restricted to maximal groupoids, we obtain the original map, and such that it has this universal property that mapping into it is the same as whatever this is saying. So mapping into C and then factorizing over the full subcategory, and that's supposed to be in equivalence, right? So it's almost 90 minutes.
I have a question.
Think. Yeah.
When you say homotopy monomorphism, is that different from a monomorphism that you have defined before?
No, I always meant homotopy monomorphisms, and in some slides I forgot to write it down, but it's monomorphism so always meant to be monomorphism, homotopy monomorphism. Yes. It's just,
you could write if, yeah, monomorphisms of groupoid J from X to, okay.
Yeah.
Okay, so subtype former.
Yeah. So I think next week what we'll do is continue is doing fibrations, and then again these deformation retracts will play a central role. So so far we only have yeah.
I want to make sure I understand what is this fall. It means essentially that you given a full subgroupoid of the groupoid of the core of a category, then there is a corresponding full subcategory. You want to have kind of a bijection between the full subcategories of C and the full subgroupoid of the core of C, or something like that.
Yes. Yes.
And that's an axiom for being able for doing that.
Yes. Yes.
Okay. Thank you.
And for instance, with that, we can form the essential image of a functor, for instance.
I'm sorry.
I said that a consequence of this axiom is that we can speak of essential images of a functor, of a map.
I see. The full and faithful image somehow.
Yeah, exactly. We take the full subcategory in the codomain whose objects are the guys which are isomorphic to something in the image.
Yes. Okay.
And we want this to be available.
Okay.
As a type constructor.
Okay. Thank you.
Yeah. So yeah, so for next time, so really what we only talk about today is like isofibrations, and what we want to do in the end is kind of dependent type theory, and these isofibrations is really just dependency on the isomorphisms, and we would like to have really taking into account that we can have push forwards and pullbacks along morphisms, non-invertible morphisms. So next time we'll define what are Cartesian, co-Cartesian fibrations and the groupoidal variant of this. And for this, again, this will come from the interval. And the point is that, so there's a characterization of fibrations in terms of certain functors having fully faithful left or right adjoints. And again, so that's where this deformation retracts or reflector or co-reflector that was suggested come into play. This is something that we can define right from the start without really saying that we have adjoints, and that should be enough to define the right notion of fibrations, and then go on further from there. But I think that's a good place to start.
Okay.
Thank you very much.
Thank you.
Okay, very nice talk. The floor is open for questions now.
I'm tempted to ask a question to Steve Awudi.
Okay,
Steve,
well,
Steve,
sure.
what do you think of that stuff?
I've seen a few other similar attempts or experiments or theories. Like I'm thinking of the one of Jonathan Weinberger, who's also here, I think, and some others. I wonder, how far do you expect to get? I mean, I think Jonathan and Ulrich Buchholtz have made it quite far, but there are some obstacles. You seem to be suggesting you're going to get farther. Is there some reason why you think it's not a principled obstruction? It's just a matter of getting the basics set up the right way, and then you can go further? I think they were having some difficulties with the universe of vibrations or something.
We won't have any difficulty with universes. So the principle is that we will go very far because we give a lot of axioms. We admit as fundamental truths a lot of non-trivial results. If you want to prove that you have a semantic interpretation of what we do in classical mathematics, it's at least 200 or 300 pages at minimum, as far as I know of. That is, you see, it would mean that if you open a book on quasi-categories, for instance, you will learn all the basics, like essentially to the axioms we discussed today. But then eventually you have to know all the theory of Kahn extensions and colimits, free completion by colimits, a theory of presheaves, and so forth. And if you assume all that far enough, then you can do a lot. And the reason why I'm very confident we can essentially, so I gave a list of things I would like to do in the introduction. I'm very confident we can just do them all because and now there is also a lot of literature about internal infinity one category theory in an infinity topos. And this literature is already doing all of the program I propose. And essentially what you can do in any infinity topos should be quite close to what you can do formally. That's what I believe. And so I also have the experience. I'm confident that many of the proofs I know firsthand, they can be done formally. And I'm also quite confident that what we can do in any infinity topos can be done formally. But again, we have to realize that the list of axioms we give is really a lot. We don't start from zero at all. So the idea is to formalize in the computer a long list of fundamental truths.
Yep.
And then out of that, we do something new. And so to prove, for instance, that starting from scratch, like for ordinary homotopy type theory or whatnot, you could formalize everything we are saying today would be a lot of work. But the idea is that what I say is that we don't have to wait for it. We could also try to formalize it right now and prove theorems of category theory formalized in computers now. Don't wait for foundations starting from scratch.
Yeah, so you can work axiomatically or synthetically by stating your stating your axioms in dependent type theory with some enriched with certain additional primitive structures like the interval and so on, which are also presented axiomatically. And then you work from there. It's not necessary to try to verify the soundness of everything by building models in Simplicial sets and so forth. You don't have to do that.
No, I said this is the theorem that everything is sound in Simplicial sets and so forth. That's why this is why we very freely add as much axioms as we need, because as long as we know they are true, and so the fact that they are sound, it's just a theorem. So we just take them for granted.
Right. Very nice. Yeah, it's very nice. It's a good approach, I think.
So I have a much narrower question, but it's kind of related. So in this slide here, I'm wondering what is the map from fun AC to fun from the core of A to the core of C?
Yeah. So this one right here, right? Yeah. So I mean, this is an adjoint. So it's produced using units and co-units, probably co-units. That I don't know.
Yeah,
I cannot write down.
Maybe I'll say the reason I ask is I'm
Okay.
pretty sure in the like quasi-categories model, for instance, that right adjoint is not enriched. So, you know, at the level of the, you know, the level of the vertices, it's no problem, but at the level of the higher stuff, it doesn't exist. What you can map out of is if you put a core on the exterior of the fun AC.
Yeah, I think you're right, Emily. There is a missing core.
There's a missing core
Externally.
Okay.
Maybe I should have put cores everywhere. Is that true?
Because also when you say it is an adjoint, I think we mean that we have a notion of mapping space, which consists to decorate the functor category and take the maximal group within it and so forth. And we have to
I think that's what you mean, right? We should have everything here.
Yeah.
That's right.
Yes.
Yes.
Okay. Thanks.
Yeah. I forgot that.
Sorry, maybe a related question. You sort of sketched at the beginning some intended models of this whole setup. I'm wondering how rigorous that is or will be.
As I said, the way I wrote my book and the way we wrote our paper with Kim is designed that it will be literally true for quasi-categories. And I didn't write it completely, but I think it's not very different to do it for complete Segal spaces. And then I think it will be the same, exactly the same method as Mike Shulman's proof should say that if you take at least complete Segal spaces in a higher topos will be literally a model. Because the thing is, the main difficulty will be again to rectify universes, but I think Mike's shown us the way.
Maybe a related question, since you mentioned complete Segal space, you are showing that for every object you get an associated Segal object.
Yes.
Can you also prove from the axioms that you already have that it is a complete Segal object?
Yes. In fact, it is a reformulation of the axioms. Because you see, the idea is that you have a type, and therefore you can take its Dwyer-Kahn localization, and now you can take, and because we have all the simplices, so you can take the mapping space from any simplex to your type, and then give you a simplicial space, ordinary space. Yeah. And now the last axiom that not the full circuitry axiom, but the previous axiom that Kim was discussing is essentially saying that this simplicial object is complete.
You mean this axiom here? Yeah,
there was the Segal axiom, which was saying that it is Segal.
I see.
And this is saying it's complete. It is literally the same thing, in fact. Or I say literally, I mean, I think you want to apply it not only for C, but to any functor category or something like that. But yeah.
So you're saying that any category is equivalent to the category of isomorphisms of it or someone. I'm thinking of iso invert C or is invert as the category of isomorphism of C.
Yes. Yes.
Not the groupoid of isomorphism, the category of isomorphism.
Yes. It is what it is. Yeah. It is a category of isomorphism, and as such, it is equivalent to C. Yeah.
Okay, and that's you're saying that's that shows that C is a complete Segal space. Oh, good.
Yeah. And so what it is saying also is that, you see, we started from a type, so we had an abstract notion of identity type that did accept. And now, because of this axiom, we have a new identity type, which is very explicit, which is built from the interval, which is this invertible maps. And that means now, every time we do homotopy pullbacks or whatever, we can take this identity type instead, for instance. And also because we did introduce the full subcategory axiom, we can also replace this by the full subcategory of the C2Z delta 1, whose objects are invertible maps. It will be also an identity type. So we have all these things we can play with. And our axioms will prove, will have as a consequence that every type will be a complete Segal space. Like we can prove that the universe will be equivalent to a localization of the universe of group of the Simplicial objects, because the delta will make sense. So we will be able to speak of the universe of Simplicial objects in the universe of groupoids. And we're able to prove that the localization of that will be the universe of types, of categories. And this localization will be, in fact, exactly the description as complete Segal spaces. So it means internally, the fact that we can describe any category as a complete Segal space will be just true. And therefore, we can also put back ordinary homotopy types at the center if we want. But it is a Lovier kind of version. So we start from category theory as a basic notion, and then we reconstruct everything out of that. Yeah? And it's very Loverian because it's a one category of categories. Yeah? And then we construct everything.
Okay. Very nice. I like the fact that you're constructing delta somehow has a monoidal category, because this was, of course, an observation of Lovier that delta plus is the monoidal category freely generated by a monoid, and somehow it's part of the picture.
Yeah.
Yeah.
Any more questions, remarks?
Yeah, sorry, I do have another one. Apologies.
Sure,
Could we go back to the Segal condition slide?
Yeah.
Right. I don't understand the codomain of the first map. Is that meant to be the matching space, or is I just don't understand what that is. Oh, sorry, this is the relative thing. Okay. So I know I asked about this already, but I still don't understand.
There are two assertions there. There is a general way to produce isofibrations by restricting to some place maps. And then a second assertion, which is say that out of that, we can produce a Segal map, which will be an isofibration as a consequence of the first part of the assertion. And the last part, and then we claim as an axiom that this Segal map is an equivalence.
Right. So
I don't know.
Yeah. So it's actually the first condition that confuses me and not the second. And
okay, so the isofibration thing. Okay.
Yeah. So what I would have expected here is essentially the matching space instead, the full boundary. So I realize you don't have colimits.
Yeah,
so
you like the full boundary and not that only. And you are worried that, okay.
So I'm wondering if this is, I mean, if this is the same strength, that's something I don't know, and I would love to know, but it feels weaker to me.
I understand that. Okay, I should check it, but I think it's the same strength.
Okay. Well, if you'd send me an email with that, I would love to know that.
Okay, I will try I don't claim I wouldn't. I don't claim I am able to prove the same strength for an arbitrary D category. So, but for something nice like delta, I think the same strength is what I mean.
Maybe a related question: if you take your axioms and you take an arbitrary object y, and you slice over y, of course, the tribe sliced over y will not satisfy all these axioms. But if you restrict the slicing over y to isofibrations, of course, right? For example, minimally, you look at only the objects over y such that the structure map, let's say like P is an adult fibrations, will you have again a tribe satisfying all the axioms or not?
No, we won't.
Okay.
That's the point. You see, the reason why it's also related with the fact that we don't take the full dependent type theory. So we don't have all dependent products and so forth. So it means that it won't be dependent in the classical sense. In some sense, if you want to be dependent, what you would like to say is you can take a non-full subcategory of the slice whose objects are co-Cartesian fibrations, for instance.
Okay.
And you take only the co-Cartesian preserving, the functor which preserve co-Cartesian edges. And this will be, we satisfy the axioms, but actually, to be honest, actually, it will satisfy them only up to weak equivalence now. At least is where, at least the dependent product part will only exist up to equivalence. But the idea is that we could also have done everything up to equivalence to begin with. But the thing is that, so in practice, the absolute versions are strict the way we describe them today. And also because we can go back and forth between the language and the universe, you can really prove that all the rules you describe, you prove them in the universe. And then they translate immediately to rules up to equivalence in this relative setting. But the type dependency will be about co-Cartesian fibrations. And this will also affect the way you write the syntax also, because you see it won't be true that a function will be determined by its value on points. And all these problems have to do with each other. So you have to take that into account.
Okay, thank you.
You're welcome.
More comments? Well, if not, we're going to wait until next week to have the rest of the axioms. And we're very curious to learn about Cartesian and co-Cartesian objects.
How many more axioms do you have?
I don't know. I think all in all, it's around 20 axioms or something.
20?
Yes. As I said, we are not afraid to add them as long as they are true.
Yeah. Maybe just a remark is that Euclidean geometry has something like 19 axioms.
That's okay then. We just are.
Yeah, you're
So that's very
not too far. Yeah, it's good.